All right, everyone. Today we're going to be talking about what if the head and the tail pointers, instead of pointing at null, they point at something else. And so there's three kind of cool things you do with linked lists that involve the head and the tail pointers not just pointing off into the void, into the abyss, right? So let's say we've got a linked list that's got 10 and his next and his previous. One note. Come on, one note. Thank you. Very cool. All right. So 10's pointing at 22. Who's pointing at -7? Who's pointing at 66? And tail is pointing here. Head is pointing here. These are members of the linked list class, right? And then we've got a node class that handles each one of these individual things. So the guy that we call head, his previous pointer is pointing at null, and tail's next pointer is pointing at null. Also, so there's three kind of cool things you can do if you don't want those pointers just pointing at nothing. What you can do is you can have them point at each other, for example. So the next on tail can point to head, and the previous on head points to tail. And now you've got something called a circular linked list. So you just go to the right, go to the right, go to the right, go to the right, and then you're back where you started again. This this is very good when doing initiative systems, right? So in a video game, if you have like a turn-based video game, you'll typically sort the people based on their speed, and then have the fastest person go first, then second fastest, third path, and then you get to the bottom, and then it goes right back up to the top again. So you don't have to really special case anything like worrying about going off the edge of the linked list. It's just, oh, Mr. 66 finished. Next, 10. And you just keep going until all the monsters are dead, or all the players are dead, I guess. Maybe not the players. The players' characters are dead. In Dungeons and Dragons, it's generally frowned upon to kill the players at the table. Killing their characters is okay, but killing the players is generally frowned upon. And so you can still have a head pointer, you can still have a tail pointer. And that's pretty useful because then, I guess the tail pointer is maybe a little bit, pointless at that point. But it's still useful because now you know this is first in initiative, 66 is last in initiative, and you get to 66, and now it's time to like do any of the end of turn effects. And then when we get to 10, we can do any of the beginning of the turn effects and that kind of stuff. Shadow Heart, yes. Thank you, Git, for spamming me like that. So, no. I don't know what happened here. No, that's Rogue Trader. Yeah, there we go. It's over there. There we go. There's Shadow Heart. Right. So if you've played Baldur's Gate 3 or something like that, you've seen this kind of initiative system. Okay. All right. Any questions about that? It's pretty straightforward. You just hook the head and the tail up instead of having point at null, and you're good to go. It's pretty straightforward. Now, second thing you do with your head and the tail's next and head's previous pointers is you can have them point at a special node called a Sentinel. Okay? And the reason why we do this is so that we can get range-based for loops. Don't talk and type at the same time. For loops, range-based for loops, right? And so if you have the standard library linked list class and you ask for a iterator pointing at the beginning, which one is it going to point to? What do you think? We've got option A, B, C, D, E, and F. If I say linked list, give me your .begin iterator, an iterator is like a pointer, more or less. What is that iterator going to point at? Which letter here? If I say list.begin, who's he going to point at? He's going to point at B. Is correct. Okay. So begin will point at that. And when you do a range-based for loop, when you say like for int x : list or whatever, it generates code for you that says starting at the beginning, going to the end, but not including the end. Once you hit the end, you stop. print all the numbers or something like that. So it would print 10, 22, -7. And if I ask for list.end, which letter is that going to point at, do you think? E? E is the last element in the list? Wrong. When you call list.end, it does not point at 66. List.end points at F. So it points at a value after the end of the linked list. That's why it creates these Sentinel nodes, so that it has something to point at. Because when you do a range-based for loop, the thing pointed to by end is not included in the range. So if I give it a range, a pair of pointers, saying sort everything from here to here, it would only sort 22 and -7. It would not sort the 66. If you pass it a pair of iterators, the thing that's pointed to at the end, let's see, my fingers are reversed here. Okay, so this is C, this is E. It does not include E. You're pointing at E, but it does not include E. It's the half open range pattern. It includes C, it includes D, it does not include E. Okay. Why though? Because that matches how we do for loops, right? For int I equals 0, I is less than 10, I plus plus, it does not include the 10. That's the pattern. It includes the 0, does not include the 10. In algebra, you might have seen these things before. So square bracket in a range means that it includes the number listed there. So if you say print all the numbers from 0 to 10, like this will print the numbers from 0 to 9 in algebra. And this half open code pattern includes the 0, doesn't include the 10. That's the same pattern we use when we use iterators. So if you want to print all the numbers in this linked list here, you pass in the first iterator is going to be begin. The second iterator can't be 66. It has to be past the end. And the reason for that is like, how do you, like if you had only one element in the linked list, think about this, Lamar. Imagine you've only got one element in the linked list, and begin points here, and end points here. Right? How do you know what I mean? Like, how do you indicate if you want to print it or nothing? You know what I mean? Like, there's not, the reason why we have the Sentinel node here is so that we can say, yes, we do want to print 50 instead of printing nothing at all, which is, if you pass in a pair of iterators pointing at the same thing, then it does nothing, which is what you need if you have an empty linked list, right? Where they're both pointing at nothing, then it doesn't, So you have to, there's actually good reasons for these things, right? If they both point at the same thing, that means don't do anything. And like if they're both pointing at the same Sentinel node, then don't do anything. And this is true for vectors. It's true for linked lists. It's true for binary search trees. So, Sordarelli, does that make sense? Why we do this? Because otherwise, it's like, do you know, where to print or not? Should we print the last person or not? Okay. So, what if we wanted to print a list in reverse? So obviously we need the Sentinel node here to indicate that when we get there, we're done, right? You print the value, you go to the next. Are we done? It's a Sentinel. Yes, it is. We're done. You can't do that if the value is one that you need to print. It's kind of what I'm getting at. That's why you have to go one pass, right? Should we print this guy? Well, he's the last one. Should we print it? No, we're done. Stop. What if you want to print a reverse? What if you want to do a reverse print? Print 66, -7, 22, 10. How do I get an iterator pointing to 66 that goes backwards? Does anyone know? Olson? How do I get an iterator pointing at E that when I plus it, it goes backwards instead of forwards? You just get the tail. I could, but then if I go plus, I'm going to go to the right. So as it turns out, there is something called list.reverse begin. Okay. And list.reverseBegin points at the last element in the linked list. And then when you say plus plus, it goes here, plus plus goes here, plus plus goes here, plus plus goes to the Sentinel over here. And this is called list.rend. Not like the rending attack of a troll, claw, bite, rend. No, that's reverse end. And so if you pass in a pair of iterators, one that's reverse begin, one that's reverse end, then it will print the whole list out backwards. And basically you can do this with anything. Like when you do sort, instead of needing a custom sort function to sort things backwards, you just pass in reverse begin and reverse end, and then it'll sort the thing greatest to smallest instead of smallest to greatest. You guys understand? So reverse begin, reverse end, very useful stuff. I'm kind of disappointed, though, in your CSI 41 professor not having covered that before. Who? Oh, wait, that's me. Yeah. So that's why there's like a Sentinel node created here, a Sentinel node created here, because you keep going forward, you keep going backwards, which is forwards. Keep going backwards. Is this my end zone? Nope. Okay, print it. Go forward, backwards. Again, is this my end zone? Yep. Stop. And so when you hit the Sentinel, you stop. You don't print it. Yeah, good stuff. That's if you want to look at list rend and our begin and stuff like that. I think rend's just a cool name. I just like that. So if you've got I don't know, vector or something like this, then the reverse end is a Sentinel node on the left side, end is a Sentinel node on the right side. Okay. And it doesn't have to be allocated sometimes, but oftentimes it is. So reverse begin to reverse end prints a vector backwards, begin to end prints a vector forwards. So, okay. What is interesting? Okay. Here's a what? No, open resty. Okay, whatever. Yeah, so you can see here begin to end is one past the end. Reverse begin is the last element. Reverse end is one before. Okay. All right. And so the other thing we can do with our head and tail pointers is we can merge them to another list. Sounds like you're tearing the list in half. I know, like you're rending it, right? Now, this brings us to the star, why a linked list, which is a great question because the answer is usually no. Like if somebody asks you, like, should I use a linked list for this? The answer is usually no. Like it just is. It's not always. It's not like a C-style array that you should just never use, like unless, there's extremely rare circumstance. Linked lists, they come up. They come up, but just not a lot. Not a lot. One of the best reasons to use a linked list is merge. If you have a bunch of things in one list and a bunch of things in another list, and you merge them together, you do this faster than basically any of the other data structures we're going to cover in this class. So let's do a little comparison, right? Let's say you've got a vector, and the vector's got data 10, 20, 30, whatever, and the vector is of size n. And then you've got another vector, and that vector is of size m. So you've got, I don't know, vector 1, you got vector 2. These are very clever names, by the way. And they've got data in them and stuff like that. Okay. So if you want to combine these two, if you want to sort of combine the two vectors together, then how many operations would it take? Like, let's say that you're going to just, you're going to do this by doing pushback, right? Like you're just going to take all the elements in M and just kind of like add them all to N. What is the big O running time of this? If you want to add all of the elements from vector 2, there's M elements. If you want to add all M elements from vector 2 into vector 1, how many operations is this? Big O of what? N plus M? We have a vote for N plus M. Do we have to, like, we're just going to add them to vector 1. We're not making a new guy. If we were making a new guy, yeah, the order n plus m for sure. But if all we have to do is add vector 2's guys to vector 1's like this, then all we have to do is do order m pushbacks, and then we can free vector 2. So we've copied 2, 3, 2, 1. Yeah, we've copied all the elements over. So this is going to be an order m operation. Yep. So we just iterate through m and call pushback. Each pushback is order 1 amortized. So this works out to an order m merge. And this is, generally speaking, what you're going to get with most data structures. Like for most data structures, if you're going to take everybody in one data structure and add them to the other one, the best you can do is order m, because you just have to go through the whole thing, just toss them in the other guy. But not linked lists. So linked lists are fast at this, okay? So if you've got, let me drop a little linked list here. Oh, drop a little linked list here. And we got 10 and 7 and 5 here. So his head pointer is pointing at null. And then we got another guy over here that's 11, 22, and 33. And his tail pointer is pointing at null. His tail pointer is pointing at null. His head pointer is pointing at null. His head previous is pointing at null, I should say. And tail's next is pointing at null. I can merge these guys together with just a few operations. So if I want 11 to be glued to the end of list 1, so we got list 1 over here. And we got list 2, again, very creative names over here. If I want 11 to be tacked to the end of 5, what should I set tail points to next to? Tail points to next equals, let's call this head 1 and tail 1. Who knows? Head 1 and tail 1, we got head 2 and tail 2. Okay. So tail 1 points to next equals what? What do you guys think? How do I make it point to head 2? Tail 1 next equals head 2, just like that. Good. So that, in ink, it's going to look like this. I always like drawing linked lists because every time you draw something, that turns into a line of code. So tail 1's next is going to point to head 2, just like that. And then you can look at this thing, you'll be like, oh, we need to fix up that guy. So head 2's previous needs to be set to what? Head 2 points to previous needs to point to who? What do you guys think? Tail 1. Head 2's previous points to head 2, you're going to get in trouble there. If head 2's previous points to head 2, it's going to look like this. Yep. So when you're going backwards, you're going to go into infinite loop. So head 2's previous needs to point to tail 1. And that's pretty good. That's pretty good. We can effectively discard tail 1 and head 2. I mean, I guess we'll just do this. We'll say tail 1 equals tail 2. If that makes sense. Because we're adding everybody to list 1. So basically tail 1 is now pointing here. Head 2 is going to go away. There's only one other invariant that we need to preserve. So, Sardarelli, what other thing do we track in a linked list? Head always points at the first element, tail always points at the last element, and then we have one other member variable that we've been keeping track of this whole time. Do you remember the thing that we keep track of when we're talking about a list? We need one more line of code here to make this correct. Not quite. Size. Okay. So we had 3 before and 3 after. What should the size be now? Did it? Software. So size. So if we had n elements before and we have m elements now, what should the total size be after we've merged the two lists together? Size 1 plus size 2. Yep, so size 1, what? What's going on with this? Size 1 plus equals size 2. You guys understand? Size 1 plus equals size 2. 4 lines of code. Note that if we had 1 billion people in the first list and 1 trillion people in the second list, this would not take any additional time. We just have the tail of one's next point to the new guy's head, the new guy's previous points at the old guy's tail. We move the tail over and add the sizes together, and we're done. That's it. We might set like head 2 equals tail 2 equals null. Like we might do something like that just to make sure they're not pointing at anything anymore. We don't try destructing them. Probably set them to null so that when they go away, they're just like, oh, we're an empty list. And then they just poof without wiping out part of our list. Okay. So that is an order 1 merge. Okay, so why a linked list? Because you get order 1 merges. Yep. We'll put a little rainbow pattern around this. Order 1 merges. Okay. So if you need to do merges a lot, then linked lists are actually a good option. Right? Like the what is the one thing that linked lists do better than vectors, like merging? What are the one thing that BMW drivers can't do? Merging, right? What is the one thing that drivers in San Francisco and Los Angeles can't do? They can't do a zipper merge. It's impossible for them. You're driving down the street, 2 lanes come into one, they just go bumper to bumper all the way in. You're like, what am I going to do now? I can't merge. I'm going to die. There's a concrete median shoving me into your lane, and you're just like, this is my lane. I don't want you in it. Like, they don't understand the concept of merging. It is absolutely ridiculous. So merging is like the one thing that linked lists can do that Los Angeles drivers cannot do. No, sorry, that pretty much any other data structure, like at least in this class, is not going to have order 1 merges where you can just combine them all and then print them all out, or whatever. So that's good. The other thing they're good at is inserting in the middle of the linked list, but to get to the middle of the linked list, you have to go n steps to the right anyway. So it's you got an order n in there anyway, which sometimes it'll be a net win, but generally speaking, if you could go n steps to the right, then you could like move all the elements in a vector n steps to the right. You know what I mean? Like it's mostly a wash for inserting in the middle. It is technically better though. People that break and merge a quarter mile back when there's a whole empty lane. Yeah, everybody gets out of the merge lane, and they get mad at you when you just drive down the empty lane and merge when the thing ends, because that's what you're supposed to do. Everybody's supposed to just drive to the end and then alternate cars as the 2 lanes come together. It's not a hard concept. And yet it just seems to just baffle and confuse these people that have somehow passed the DMV driving test and written test. Yeah. yeah. LA people, like, come on.